Welcome, curious minds, to another deep dive.
Great to be back.
This is where we really try to unpack the most critical insights from, the cutting edge of AI and machine learning research.
Mm-hmm. Cutting through the noise.
Exactly, trying to deliver those crucial aha moments for you. And as always, our focus is squarely on the technical details, the practical implications.
Yeah, the nuts and bolts of how this stuff actually works and what it means for building real systems.
Today, we're embarking on, well, I think it's a fascinating journey right into the heart of how AI systems understand language.
Deep into the embeddings.
Specifically, how we can make them even smarter, more specialized, and interestingly, potentially more efficient too.
That's right.
We're talking about custom embedding models as foundational components, really, but powering so much modern AI.
Especially the retrieval-intensive systems.
Yeah.
Like the RAG setup so many people are building now.
Exactly. If you're working with ARG, this is definitely for you.
Indeed. And we've gathered some really excellent source material for this one. It lays out not just the what, but really digs into the why and the how of tailoring these models.
So our mission today is to distill the core challenges, the strategic advantages.
And give you a clear roadmap, understanding when fine-tuning makes sense and how it becomes, well, a real strategic advantage.
Like getting a super-powered lens for your data.
Exactly, a bespoke lens. Letting your AI see nuances, relationships that might otherwise just be invisible.
That's precisely the kind of granular detail our listeners are after. So before we jump into the how, maybe just quickly level set for anyone newer to this.
Sure.
What is an embedding model, just fundamentally, and why does fine-tuning even come into the picture? Let's unpack that first. Okay, so starting at the beginning, these off-the-shelf embedding models,
Right.
What are they doing? What's their primary role?
Right. So at their core, these models, often using sophisticated architectures like transformers, their job is to turn text, complex language, into numbers.
Into vectors, right. Dense numerical vectors.
Exactly. Dense vectors. And the magic, really, is that these vectors aren't just random numbers. They capture semantic relationships, meaning
So words or phrases that mean similar things end up close together in this high-dimensional space.
precisely. It's mapping language into a space where meaning dictates distance. That's how machines start to understand context, nuance, beyond just keywords.
Okay. And the pre-trained ones, the off-the-shelf ones, they're trained on everything.
Well, practically everything. Huge general data sets, think Wikipedia, massive web crawls like Common Crawl, vast collections of books.
Looks corpus, things like that.
Yeah. The goal of that huge initial training is to give them a really broad understanding of language.
Yeah.
Common words, phrases, general relationships between concepts that appear, everywhere.
So they're like general encyclopedias. They know a lot about everything, but maybe not the super specific stuff, which raises the question, even with all that data, why is it so hard for them to get those niche domain-specific details? Is it just data volume or something else?
It's definitely more fundamental than just volume, although that's part of it. They're great generalists, right? They understand common patterns widely.
Right.
But their limitation is that this general knowledge often just doesn't capture those company-specific or domain-specific nuances effectively.
Because those nuances weren't really in the training data, or not enough.
Exactly, or not represented in the specific way they're used in your context. Imagine an off-the-shelf model trying to understand, say, the internal jargon of a specific law firm.
Or technical specs for some proprietary component.
Right. When the model misses these specific relationships, maybe it can't tell apart two terms that sound similar but mean totally different things in your field.
Or it fails to see a connection between two terms that are actually highly related in your domain.
Then your retrieval performance just tanks. And that becomes a critical technical bottleneck because the quality of what you retrieve directly depends on the model spotting these subtleties.
It's that problem of words having multiple meanings, or multiple words for the same meaning.
Polysemy and synonymy, yeah. But specific to your domain, which the general model just hasn't learned to handle in your context.
Can you give us some really concrete examples? Where do these general models fall short in a way that really hurts a system? What are the pain points?
Oh, absolutely. Think about highly specialized fields. Legal documents are a classic example.
Okay.
In law, discovery isn't just finding something new, it's a whole legal process of exchanging info.
Right. Very specific meaning.
And brief isn't just short, it's a specific legal document summarizing a case. A general model might completely miss that, pulling irrelevant stuff if a lawyer searches discovery documents.
Okay, I see. What about medicine?
Medicine, too. Stat means immediately, which is obviously critical.
Hmm.
A general model might not prioritize that urgency or link stat correctly to critical procedures. Or think manufacturing. Internal docs might talk about a bill of materials, right?
A highly specific list.
General model might think explosion, sound effect. Exactly. Completely missing the industrial context. Or in finance, derivatives, complex financial instruments. A general model might also see the linguistic sense, like deriving a word.
That ambiguity leads to irrelevant results, wasted compute, higher latency.
And it just diminishes the value of your whole RAG-E system. The model fundamentally lacks that deep context that only comes from seeing your kind of specific language over and over.
It hasn't learned the unique patterns, the subtle shifts in meaning within your data.
Precisely.
So, okay, there are some domain-specific models out there. You can find them on leaderboards like MTEB, right?
Yeah.
Finance models, medical models. But even those might not be enough if your niche is super specialized or you have unique company jargon. It's like having a finance dictionary, but your company uses its own internal slang for products or processes.
That's a really crucial point.
Yeah.
It hits the inherent limits of even pre-trained domain-specific models.
Right.
A general MTEB financial model might be great for standard finance terms.
Right.
But if your company uses proprietary terms, internal codes, specific project names,
Like Project Nightingale for some initiative or FX2000 for a specific derivative type.
yeah, the generic financial model has absolutely no way of knowing what those mean or how they relate to other concepts within your organization.
Because they weren't in its training data in that specific context.
Exactly. Its vector space, that map of meaning we talked about, just hasn't been shaped by the very specific relationships that are critical for your business. The gap widens right there.
So if our off-the-shelf model, even a domain-specific one, isn't cutting it, what are the actual tangible technical benefits of going through the fine-tuning process beyond just smarter? What does it do?
Okay, the primary benefit, the one you'll likely see most clearly, is a direct, measurable improvement in retrieval performance.
Better search results, more relevant documents found faster.
Yes. When your embedding model truly understands your specific domain, maps your jargon correctly into that vector space, it just retrieves better stuff. More relevant, more precise.
And that directly impacts downstream tasks, like in a RAG.
Absolutely. Think about it. If your retrieval pulls garbage, or just irrelevant stuff, what's the generator going to do?
Garbage out. Or hallucinations.
Exactly. A precisely tuned embedding model drastically cuts down that noise. Fewer irrelevant chunks go to the LLM.
Which means better answer quality?
Huh?
And maybe helps with the context window? Less junk filling it up.
Precisely. You get more grounded, accurate, trustworthy AI outputs because the foundation, the retrieval, is stronger.
Okay. Better system performance. That makes total sense. But you also mentioned cost and latency benefits. That still feels counterintuitive. Surely training costs more.
This is maybe the most surprising part, but it's a huge potential win. It's a bit of a paradigm shift, really. Think surgical precision over brute force.
Okay.
Instead of just throwing a massive general-purpose model at your problem, you use a precisely fine-tuned, often smaller embedding model. It becomes your specialized scalpel.
Cutting through the noise, focusing only on what matters in my data.
Exactly. And that doesn't just boost accuracy. It unlocks potentially huge efficiency gains. A smaller model, even fine-tuned, has fewer parameters than a giant general one. Fewer parameters mean
Lower memory needs during inference. Faster computation on the GPU.
right. Lower memory footprint, faster compute times, ultimately reduce latency in your applications. You might get better performance on your specific tasks, but with a smaller, cheaper model.
So I can maybe run inference using something like a MinLM model instead of a big BGE or OpenAI embedding model for my specific domain and get better results and save money.
That's the potential holy grail, yes.
Yeah.
It's a massive technical advantage for deploying at scale, especially where latency and cost really bite. It's about optimizing that precision recall trade-off specifically for your domain, not just using the biggest hammer you can find.
Okay, so if custom fine-tuning offers these potentially massive benefits, better results, lower costs, should we just jump straight to it whenever retrieval isn't perfect? It sounds pretty compelling.
Definitely not, no. This is a really critical point our sources emphasize. Fine-tuning is not a silver bullet, and often it's really not the first thing you should try. Poor vector search performance can come from so many other places in your pipeline besides the embedding model itself.
Right. It could be something else entirely.
Absolutely.
Yeah.
You absolutely must debug your whole RA pipeline or whatever retrieval system you have First, methodically check other potential bottlenecks before you commit the resources, time, compute, expertise to fine-tuning.
Because jumping straight there without diagnosing properly.
It's a classic ML pitfall. Wasted effort, frustration, and often you end up with no real improvement anyway because you weren't fixing the actual problem.
Identify the true bottleneck first. Don't just assume it's the model.
Exactly.
So this diagnostic phase sounds crucial for listeners maybe, pulling their hair out, troubleshooting a RAG system that's not quite working. What are the first practical steps, the key questions to ask before even thinking about fine-tuning?
Okay, let's break these down. These questions really help you pinpoint the nature of the problem, which then points you to the right solution. First question, do your queries often need exact keyword matches?
Okay, like product codes, specific names, error messages.
Exactly. Specific SKUs, internal codes, unique identifiers, precise names, even dates. If your users search for those and semantic search isn't finding them well,
Fine-tuning might not help.
it might not be the first thing to try. Semantic search is great for concepts, but sometimes iffy on exact lexical matches, especially for rare stuff.
So what's the alternative there?
Keyword search, or better yet, hybrid search. Combine semantic search with traditional keyword matching, like TF-IDF or BM25.
Right, get the best of both worlds.
Yeah. It avoids heavy computation for what might just be a simple string matching problem. Why use a neural net if grep plus semantic gets the job done?
Pragmatic. I like it. Often hybrid search can give you a decent lift, maybe 10–20% recall improvement for certain queries, without touching the embedding model at all.
Exactly. Use the right tool. Okay, next big one. Is your data chunking effective?
Chunking. Everyone's favorite topic.
It's overlooked so often, but it's absolutely fundamental. It's probably the most common reason for poor retrieval, honestly.
Because the embedding model embeds the chunk, right? So if the chunk is bad,
The embedding will be bad, suboptimal. Your search results suffer. Think about it. Chunks might be too small, lacking context for a good embedding.
or split weirdly, like mid-sentence.
Yeah, breaking up coherent ideas.
Yeah.
Or they could be too large, full of noise, diluting the actual important information you want to find.
So experiment with chunking first.
Definitely.
Oh.
Try different strategies. Fixed size windows with overlap. Recursive chunking based on structure, like headings.
What about this late chunking I've heard about?
Right, late chunking is interesting. Instead of static chunks made when you ingest the data, it's more dynamic.
How does that work?
You might process or re-chunk the text at query time, or based on the document's inherent structure, paragraph breaks, sections, key entities.
So you create the chunk just in time to be maximally relevant to the query.
That's the idea. Aiming for maximum coherence, minimum noise for the chunk that actually gets embedded. It can really help with structured or varied content.
But the core technical challenge is still that balance, right? Enough context for the model, but not so much noise it confuses it.
Exactly. It's this delicate trade-off. Enough signal, not too much noise. It's painstaking, but getting chunking right can have a massive impact, often more than changing the model.
That's a powerful reminder. The data prep before the model is maybe even more critical.
Absolutely. Then, okay, we do look at the model, but still broadly first. Ask, is your current model failing on general nuances, not just domain-specific ones?
Meaning it struggles even with common language patterns, general synonyms, idioms.
Yeah. If the base model seems weak, even outside your niche, then maybe try a larger model first. One with more dimensions, maybe a different architecture like a late interaction model.
These might just have a richer general understanding.
Potentially, yes. Due to more parameters, maybe different training. Now, the technical implication of more dimensions.
Higher compute cost, bigger memory footprint.
Right. Higher cost, more memory, but potentially better representation power. It's that trade-off again. Sometimes you just need a better generalist before you specialize.
Okay, so keyword check, chunking check, general model power check.
And then finally, only if the model specifically fails on domain or company-specific relationships is fine-tuning the likely answer.
This is the green light.
This is the green light. This pinpoints the problem directly to the model's lack of understanding of your specific world, your jargon, your acronyms, your product names, how concepts relate uniquely in your industry.
So if it handles heart attack, okay, but bombs on Project Chimera or Q3 projections V2.
And those are critical terms in your documents, yes. Then fine-tuning is probably warranted. It's that lack of specific contextual understanding that the pre-trained model just never saw.
Wow, that's a really solid diagnostic checklist. It forces you to understand the nature of the problem, not just that it's broken.
It emphasizes that technical rigor before you start fine-tuning. Saves a lot of time and compute, I bet.
Absolutely.
Okay, so let's say we've gone through the checklist. We've ruled out other issues. We're confident the problem is domain-specific understanding. Fine-tuning is the path. What about resources? Is this going to break the bank, especially for smaller teams?
Yeah, good question. And the good news is fine-tuning is way less resource-intensive than pre-training from scratch.
Okay, that's a relief.
Pre-training needs massive data sets, huge compute clusters, think hundreds of high-end GPUs running for weeks or months. It's building understanding from zero.
Fine-tuning is different.
Fine-tuning is adapting an already smart model to your niche. So for smaller base models, like maybe a MinLM variant, and smaller data sets.
A few thousand examples.
Yeah, maybe. You might actually be able to run these pipelines on consumer GPUs, an RTX 3080, 4090, maybe even the free tier on Google Colab if you're careful.
Seriously, that makes it incredibly accessible.
It really does. Opens it up way beyond just the giant labs. Now, if you need to scale up, bigger models like BGE base, tens of thousands of data points.
Right. Then you'd look at more powerful dedicated GPUs, A100s, V100s, probably on cloud platforms like AWS, Google Cloud, Azure ML, using their specialized instances.
But the total cost is still manageable, not like pre-training costs.
Generally, yes. Surprisingly low sometimes. Maybe a few dollars for simple tasks, maybe hundreds for more complex ones, rarely tens of thousands.
Why so much cheaper?
Because fine-tuning often only needs a few epochs. Maybe 1 to 5 passes through your training data. You're just making precise adjustments, not rebuilding the whole thing.
Leveraging the knowledge already in the pre-trained weights.
Exactly. Adjusting the final layers, mostly, for domain specificity. It's a surgical strike, remember, not carpet bombing. Huge technical advantage over LLM scratch training costs.
Okay, that's encouraging. Now, choosing the base model. There are so many out there. Where do you even start? Feels like a needle in a haystack.
Yeah, it can be overwhelming. The Massive Text Embedding Benchmark, MTE, leaderboard is really your best friend here. It's indispensable.
Because it evaluates models rigorously across different tasks.
Exactly. Retrieval, similarity, re-ranking, clustering, all benchmarked.
And the recommendation generally is to start lightweight.
Back to that idea. A smaller, well-tuned model might beat a bigger general one on my specific task.
Precisely. Aligns with efficiency and cost goals. Look at MTE scores for tasks similar to yours. Retrieval is key for a RAG, obviously. Maybe STS, semantic textual similarity, if your queries are short and need precise matches.
The intuition being a simpler model can specialize better with the right data, without the baggage of irrelevant general knowledge.
That's the hypothesis, yeah. And it often holds true.
And the choice of model affects how you fine-tune it, right? Open versus proprietary makes a difference.
Huge difference. Absolutely critical technical distinction. If you use open weight models with permissive licenses, all MinLM L6v2, BAI, AAIJ base on V1.5, those sorts of models.
You have full control. Immense flexibility. You can use great open source libraries like Hugging Face's sentence transformers. They give you pre-built training loops, loss functions, evaluation tools, makes it manageable, allows deep customization. You own the data, the process, the weights.
But for proprietary models, like OpenAI's Ad002 or Cohere,
you need to check their API offerings. Do they offer fine-tuning as a service? If so, you send them your data, they trade it on their side.
Less control, more convenience.
That's the trade-off. You don't get direct access to weights, maybe less control over the training loop. You rely on their managed service. Plus, potential data privacy or vendor lock-in concerns for some orgs.
Okay. Now, before we even start fine-tuning, you mentioned setting up an evaluation pipeline. Why is that absolutely crucial? It seems like extra work up front.
It's not extra. It's non-negotiable. Foundational ML practice. Think about it. Changing your embedding model means re-embedding and re-indexing all your data.
Which is a lot of work. Yeah. And cost.
Yeah. Exactly. Significant effort, compute time, maybe storage costs. You only want to do that if, demonstrably and quantifiably that you're getting better performance.
So the evaluation pipeline gives you a baseline, a number to beat.
A precise quantitative baseline with your current model. Then you can rigorously compare your fine-tuned model against it. Without that, you're flying blind. Did it actually help? Did it make things worse in some subtle way?
Prevents you from deploying something worse than you started with, or something that just memorized the training data.
Exactly. It's your scientific control. Essential.
So what does that evaluation data set look like? And what metrics are we actually tracking? It's more than just accuracy.
Oh yeah, far more nuanced. The EVIL dataset needs queries representative of real user searches and their known relevant documents from your corpus, the ground truth.
And crucially, this data cannot be in your training set.
Absolutely critical. Must be completely separate. Otherwise, you get data leakage, overfitting, and totally misleadingly good scores that won't hold up in the real world.
So you run a query, get the top K results from the model, and compare to the ground truth. Using what metrics?
A suite of standard retrieval metrics. Each tells you something slightly different. There's mean reciprocal rank, MRR.
That focuses on the rank of the first relevant result.
Yes. Great if finding one good answer quickly is the goal, like Q&A. Then you have recall at K and precision at K.
Recall is, how many of the total relevant docs did I find in my top K?
Right. Good for comprehensive search. Precision is, of the K docs I retrieved, how many were actually relevant.
Good for relevance, avoiding junk.
Exactly. Then there's mean average precision, MAP, which averages precision across ranks, giving a broader view.
And NDCG. Normalized discounted cumulative gain. Sounds complicated.
It's more sophisticated. It weights relevant items higher if they appear earlier and can handle graded relevance, like some docs being more relevant than others. Great when rank really matters.
Okay. And libraries like sentence transformers or Retrieval help calculate these.
Yeah, they handle the math. Now, choosing the metric, that's a technical decision too, right?
Yeah.
What does it tell you?
So if MRR is low, but recall at K is decent,
it means your model is finding relevant stuff, but maybe burying it down the list. Not ideal if users only look at the top few results.
And high recall at K, but low precision at K.
Means you're finding lots of relevant things, but also lots of irrelevant junk. Casting too wide a net, maybe an issue with negative sampling, or the model's too general.
Whereas high precision at K, but low recall at K.
Might mean the model is too narrow, too conservative. Finding a few hyper-relevant things, but missing other important ones. Maybe need more diverse positive examples or better handling of synonyms.
So these metrics aren't just scores, they're diagnostic signals, telling you what to fix next.
Exactly, they guide your iteration.
Okay, let's talk about the fuel for this. The fine-tuning data set itself. Quality is always key in ML. How do we actually get this data, especially for niche domains? It sounds hard.
It can be challenging, yeah. You basically have three main routes, each with trade-offs.
Oh.
1. Use existing datasets. Check Hugging Face datasets, Kaggle, etc. If something matches your domain closely, great. Saves huge effort.
But probably won't have my company's specific internal jargon.
Unlikely. So, useful maybe for a first pass, but limited for deep specialization.
Option 2.
Manual creation. Get human annotators, ideally domain experts, to mark relevant pairs, query, relevant doc, or triplets, anchor, positive, negative.
This gives high-quality, precise data, captures real human judgment.
Yes, often considered the gold standard for precision. But
Super time-consuming, expensive, hard to scale.
All of the above. You need clear guidelines, consistency checks. It's a project in itself.
Okay, what's option 3?
Synthetic generation. This is getting really popular, especially for scaling up. Use LLMs or other methods to automatically generate training examples.
How does that work? Give an LLM my documents and ask it to.
Generate questions for which a doc is the answer. Identify paraphrases. Generate plausible negative examples based on content, yes.
Allows much bigger data sets, faster.
Exactly. Though you need to be careful about the quality. Vet the synthetic data to avoid LLM weirdness or bias. Prompt engineering is key here.
How much data do we actually need? Is there a magic number? 100? 1,000? 10,000?
The eternal question. No magic number, sadly. It really depends. Complexity of the task, specificity of the domain, quality of the base model.
But rough guidelines.
Okay, for simpler tasks, maybe narrow domains with good overlap with the base model. Maybe a few hundred to a few thousand high-quality samples could be enough to see improvement.
And for complex domains, highly specialized terms, intricate relationships.
You'll likely need more. Start thinking 1,000 to 5,000 quality pairs triplets as a baseline. Train, evaluate. If performance plateaus, incrementally add more data.
And for really tough cases,
plan for 10,000 plus, maybe tens or even hundreds of thousands if it's really complex. It's iterative. Train, evaluate, add data if needed. Enough signal to learn, but not so much you overfit.
And you mentioned duplicates being an issue. I thought more data, even repeats, was good for neural nets.
That's a good point, but it's a technical subtlety. True duplicates, especially in the same batch, can mess things up depending on your loss function.
How so?
We'll take multiple negatives ranking loss, which we'll get to. It treats other stuff in the batch as negatives. if you have identical samples in the batch.
So the model gets told the same thing as both positive and negative relative to itself.
Exactly. Confusing signals, unstable training, weird gradients creates false negatives within the batch. So careful deduplication is usually a good pre-processing step, especially with batch-based negatives.
Okay, mechanics time. How does fine-tuning actually adjust the distance in vector space? It still feels a bit like black magic.
Not magic, just clever math and optimization. But yeah, it feels like it sometimes. It's all about reshaping that space, nudging vectors.
It's different from fine-tuning an LLM for generation.
Fundamentally different.
Yeah.
LLM fine-tuning is often about teaching it specific outputs or styles. Embedding fine-tuning is about shaping the representation space itself, using contrastive methods.
Contrastive methods.
The core idea is teaching the model. Given this anchor point, which of these candidates is similar, positive, and which are different, negative?
So it learns to pull the positives closer and push the negatives further away, geometrically?
Precisely. Creating clear boundaries in the vector space, which makes semantic search efficient later.
So it's learning relationships, not generating text. Different task.
Totally different learning task. It's learning a mapping function that reflects similarity, and the loss function is absolutely central here.
Because the loss function measures how well the model is doing, how wrong its current embeddings are.
Exactly. It calculates a loss value based on the current distances versus the desired relationships. That loss value provides the signal, the gradient, telling the optimizer how to adjust the model's parameters, weights, biases, to do better next time.
And the choice of loss function dictates the data format and what relationships it learns.
Absolutely. It's the engine driving the learning. Let's walk through a few common ones.
Please do.
Okay, first, multiple negatives ranking loss, or M&R loss. Super popular, very effective, especially for semantic search.
Why popular?
Simplicity. It only needs positive pairs, a query and a related context.
No negative examples needed explicitly.
Right. The clever trick is it uses the other examples in the same training batch as negatives.
So if my batch size is 32, my query is positive for its context and negative for the other 31 contexts.
Exactly. The model learns to rank its true positive pair higher than all those in-batch negatives. Makes data prep way easier, just need positives.
What are the computational benefits? No need to mine for negatives.
Yeah, it reduces dataset curation complexity massively and computationally efficient because negatives are generated on the fly from the batch.
Yeah.
Very scalable.
Any downsides?
Quality of negatives depends on batch diversity, and maybe batch size too small, maybe not enough challenging negatives.
Okay, what's next? Triplet loss.
Triplet loss. This gives you more precise control. You need triplets. Anchor, positive, similar to anchor, and negative, dissimilar to anchor.
So you explicitly tell it what's similar and what's not.
Yes. The goal is to make the anchor positive distance smaller than the anchor negative distance, usually by a defined margin.
The challenge here is getting good triplets, especially good negatives.
Exactly. Finding hard negatives is key. Examples that are somewhat similar to the anchor, making it hard for the model, but should be further away than the positive. Trivial negatives don't teach much.
Like comparing a cat to a rock doesn't help distinguish it from a small dog.
Perfect analogy. You need those close but wrong examples. People use techniques like BM25 search or even embeddings from a weaker model to find these hard negatives. It's a whole subproblem.
Okay. And the third one, cosine embedding loss.
Right. This is great when you have graded similarity, not just yes-no relevant, but maybe a score.
Like on a scale of 1 to 5, how similar are these two sentences?
Exactly. Data format is sentence A, sentence B, and a score. The loss function pushes the model's predicted cosine similarity between A and B towards that target score.
So it learns more nuanced relationships, very similar versus somewhat similar.
Yeah. Useful for things like paraphrase detection, semantics, similarity scoring, maybe recommendations where you need fine-grained ranking.
So during training, the model calculates embeddings. The loss function calculates the error based on these desired relationships.
Pulling positives close, pushing negatives apart.
Then that error signal, the gradient, goes backward through the network.
A backpropagation, yeah.
And an optimizer like Adam uses that gradient to tweak the model's parameters.
Exactly. It's this constant feedback loop. Predict, measure error, adjust parameters, iteratively refining the model.
Until you get that nice embedding space where similar stuff clusters together naturally.
That's the goal. A well-structured space where a query vector will land near its relevant document vectors. Makes search effective.
That's a really clear breakdown. So any wisdom from the trenches, best practices for someone actually doing this, beyond picking a loss function.
Oh yeah. Like any ML project, Hyperparameter tuning is crucial, often the difference between success and failure.
Things like learning rate, batch size,
Mhm.
number of epochs.
Exactly. How many times you show the model, the data, epochs, how big the steps are when adjusting parameters, learning rate, how many samples per update, batch size.
Yeah.
You need to experiment extensively.
Find the sweet spot that works best on your validation set without overfitting.
Right. Often involves running hyperparameter sweeps, systematically trying different combinations. Maybe start broad with random search, then narrow down.
Because the wrong learning rate can wreck everything. Too high, it diverges. Too low, it takes forever, it gets stuck.
Precisely. And batch size affects stability and memory use. It's a balancing act.
And overfitting, the classic ML danger. How do we guard against that, especially with maybe limited domain data?
Robust cross-validation is essential. Split your data into multiple train validation folds, evaluate on each. Ensures the model generalizes, isn't just memorizing.
Maybe use early stopping, too. Stop training if validation performance stops improving.
Good practice, yes. Prevents over-optimizing on the training set. Also, highly recommend using a model registry.
Like MLflow, weights and biases, Comet ML.
Yeah. Tools to log your experiments. Hyperparameters, metrics, model artifacts, datasets used, give you version control, easy comparison, reliable deployment.
Especially if you plan to retrain regularly with new data.
Absolutely. Lets you track evolution, revert if needed. Crucial for reproducibility and audit trails too. And finally, don't forget monitoring in production.
Because data drifts, query patterns change.
Exactly. Data drift can silently kill your model's performance over time. You need to monitor retrieval quality and potentially retrain periodically. It's an ongoing process.
Okay, so we've done the hard work. We've fine-tuned this amazing specialized embedding model. How do we actually use it in a production system, like a RAG pipeline? The source mentions Weaviate, a vector database. What's its role here?
Right. The vector database is critical for actually using these embeddings at scale. You've got these high-dimensional vectors.
Millions, maybe billions of them for your documents.
Exactly. Storing them is one thing, but searching them efficiently for similarity, that's tough.
Yeah.
A traditional database would crawl.
But vector databases are built for this.
Specifically, they use specialized indexes like HNSW, hierarchical navigable small worlds, to perform approximate nearest neighbor, ANN searches really fast.
Finding the most similar vectors quickly in that huge space makes real-time semantic search possible.
That's the key. Now, fundamentally, you can use any custom model with a vector DB using the bring your own vectors or BYOV approach.
Meaning I generate the vectors myself using my model, then just load them into the database.
Yeah. Generate document vectors, load them. Then at query time, generate the query vector with the same model, send it to the DB for search.
Maximum flexibility, but sounds like manual work in the pipeline.
It is, which is why there are often more automated ways, as the source mentions. These usually rely on having your model accessible somewhere standardized.
Like push to the Hugging Face hub?
Exactly. That's a common pattern. Weaviate, for example, offers vectorizer modules that automate the embedding generation if your model is hosted appropriately. Offloads the embedding step.
Okay, so if my fine-tuned model is on Hugging Face, how does Weaviate connect and automate this? What's the setup?
It's actually pretty streamlined. Weaviate has a tight integration. You basically just need your Hugging Face API key.
To let Weaviate access your model securely.
Right, provide that along with your Weaviate API key and instance URL when you set up your client connection, usually via environment variables or config.
And then in Weaviate itself.
When you define your data collection, your schema, you tell it to use the text2v Hugging Face vectorizer module.
And point it to my specific model.
Yes. You pass a model parameter with your model's exact name from the hub, like your fine-tuned model.
And then Weaviate handles the embedding automatically for ingested data and incoming queries.
That's it. It calls out to the Hugging Face model to embed data on import, embeds queries as they come in, then does the search. Simplifies your pipeline a lot, ensures consistency, powerful abstraction.
That sounds incredibly convenient for many setups. But what about bigger enterprise environments? Maybe running heavily on AWS. Can we use infrastructure like SageMaker?
Absolutely. Weaviate also integrates tightly with Amazon SageMaker, AWS's managed ML service. Perfect for enterprises needing robust deployment, scaling, security within AWS.
So I'd deploy my fine-tuned model as a SageMaker endpoint first.
Exactly. Package your model correctly for SageMaker. Often involves putting weights and inference code in a .tar.gz archive. Deploy it as an endpoint. You'd verify in the AWS console that it's active and working.
Then configure Weaviate to talk to it. using AWS credential.
Yep. Provide your AWS access key, secret key, and the AWS region where your SageMaker endpoint lives.
And the configuration in Weaviate is similar. Tell it which vectorizer and endpoint.
Very similar pattern. You specify text2 vcause as the vectorizer, provide the AWS region, set the service parameter to SageMaker, and critically give it your specific SageMaker endpoint name.
And Weaviate then calls that endpoint for embeddings.
Yes, securely communicates with your SageMaker endpoint for ingest and query embeddings. Gives you an enterprise-ready, scalable way to serve your model, leveraging SageMaker's features like auto-scaling, monitoring, etc.
One key technical point there, though.
Yes. Don't forget SageMaker endpoints cost money while they're running, even if idle. Manage that lifecycle, delete endpoints you're not using anymore to avoid surprise bills. Critical operational detail. #TechTagOutro.
Wow, okay. What a genuinely deep dive into the technical nuances of fine-tuning custom embedding models.
We covered a lot of ground.
Yeah, from the why, getting bow retrieval, maybe lower costs, to the crucial when, that whole diagnostic checklist before you start.
Don't skip the diagnostics.
And then the how. Dataset curation details, loss functions, hyperparameters, and finally integrating with vector databases like Weaviate, using things like Hugging Face or SageMaker.
Yeah, it's clear this isn't just a minor tweak. It's a strategic process with real technical depth.
Exactly. And it feels like something often overlooked, maybe, in the rush to build our Cray system.
I think so. But getting the embedding model right, really tailoring it, can be such a game changer for precision, efficiency, quality.
Making the AI truly understand your unique data, mapping your specific world into that vector space.
It's moving beyond general AI towards specialized, actionable intelligence for your specific needs. Engineering the semantics.
So for you, our listener, navigating this complex AML world, what's the big takeaway?
I think it's that true optimization often isn't just about grabbing the biggest, newest model off the shelf.
Right. It's about meticulous adaptation, taking powerful tools and making them truly yours through careful, data-driven fine-tuning.
Precisely. Unlocking performance that general solutions just can't match for your specific problems.
And thinking about that real-world performance, it raises a final question, maybe something to ponder.
Okay.
Beyond the technical steps we laid out, what subtle factors, maybe things we didn't explicitly cover, might impact how a fine-tuned model really performs out in the wild?
That's interesting. Like, what about specific kinds of data drift? Changes in how people query or new types of documents appearing? How would you even detect that impacting your specialized model?
Or what about assumptions baked into how you created that fine-tuning data set? Could those lead to unexpected biases or behaviors, even if your core metrics look good?
Yeah. It reminds us that deployment isn't the end. It's really just the start of the continuous optimization journey in a dynamic world.
A fascinating thought to leave you with, indeed. How do we manage these models long-term? This has been The Deep Dive. For more insights and to stay updated on the latest AI and ML research papers, do visit our webpage, neuralintel.org.
And check us out on YouTube for more deep dives like this one.
We hope you feel much more informed and ready to tackle your next AI challenge. Thanks for tuning in.